Hello.
Hey,
How's it going this week? All right. Guess we'll give it one more minute. Okay. I guess we'll slowly get started since I'll spend a minute reviewing. Um, I guess someone want to confirm you can hear me and see my screen real fast.
yes to both.
Great. Okay. So last time we discussed multilinear extension polynomials and multilinear Lagrange interpolation. And these are sort of the key notions from basic facts about multivariate polynomials that one needs to know in order to understand the state-of-the-art interactive proofs, which we're finally about to see today, notably something called the sum check protocol. So a quick review of these multilinear extensions and Lagrange interpolation. Okay, so if you give me any function defined over the domain 0, 1 to the n, which I'll often call like the Boolean hypercube or, bit vectors, so it maps any, n-bit vector to some field element. Then there is always a unique multilinear polynomial, which I typically denote by sticking a tilde over the function that extends f. And by extends f, what I mean is if you evaluate the polynomial at any point x, where the original function is defined, so that is at any point x in the Boolean hypercube, the polynomial spits out the same thing that the function itself does. Okay, so we sort of think of the hypercube as like a quote small domain. So here, if n is 2, so the hypercube is just the two-dimensional 0, 1 by 0, 1. This is the small domain that f is defined over, and the multilinear extension is defined over field by field. So there's like a row for every field element and a column for every field element. So the multilinear extension is a much bigger object in terms of its domain anyway than f itself. But of course, if you tell me f, you've also effectively told me the multilinear extension. So this is sort of equivalent to the fact that 0, 1 to the n is what's called an interpolating set for n-variant multilinear polynomials. basically if, you give me any desired, input output behavior over the interpolating set, and there's a unique multilinear polynomial with that behavior. And then Lagrange interpolation is a basic sort of fact about these multilinear extensions, which is, if I give you as input, all evaluations of some function over the hypercube, and an evaluation point r in the whole field, so r in field to the n, there is an order n time algorithm, 2 to the n, sorry. So linear in the size of the input, because the input here is 2 to the n evaluations of f, that outputs the multilinear extension evaluated at r. Okay, so it's an order 2 to the n time algorithm. That's the best you can hope for, given that, you have to at least read the input, which is, 2 to the n evaluations of f, or the thing you are extending. And like the key identity, algebraic identity that underlies this algorithm is that the multilinear extension of f evaluated at any point can be written as a sum over inputs in this interpolating set 0, 1 to the n of the evaluation of f at that point times what's called the xth Lagrange basis polynomial evaluated at the desired evaluation point. So this is xth Lagrange basis polynomial, like multilinear Lagrange basis polynomial. And the point is, this is sort of, the unique multilinear polynomial that, when you evaluate it at, if r is in 0, 1 to the n, this thing is meant to pick out x, so that, this will evaluate to 1 if r equals x, and 0 otherwise, 0 if r does not equal x, right? But so that is if you feed chi sub x a point in the Boolean hypercube, it acts like an indicator function picking out x, but you can evaluate chi sub x outside of the hypercube at any point in field to the n. And so, this is the key. People will call this equality, like, multilinear Lagrange interpolation. I use the term to refer to both this equality and the linear time algorithm that computes f total of r really quickly, given these evaluations f of x. So that's what we discussed last time. Okay. Does anyone want to ask a quick question about last time? So then let's dive into the SumCheck protocol. So the SumCheck protocol is meant to solve the following problem. So like from the verifier's perspective, the goal is to sum up all evaluations over the Boolean hypercube of some polynomial. Okay, so here G is an n-variate polynomial. Okay, and let's say, so in general, G needs to have, quote, low degree in each variable. To make things concrete, let's say it has degree at most 2 in each variable. Now, nothing is really going to change if the degree is not 2, but rather 3 or 4 or 5 or 6. So this 2 here is just for simplicity. In general, the deal is like the higher the degree of G in each variable, let's say the bigger the proofs, and the the slower, as a result, the slower the verifier, and also, the slower the prover. But there's a caveat, which the caveat is, that's assuming, for a fixed number of variables n. But, so sometimes you can make, by increasing the degree of G, you use a different G that is higher degree in each variable, you're able to reduce the number of variables that G is defined over. And so there's a bit of a tension where higher degree means bigger proofs, like in each round of the protocol, but fewer rounds. And, sort of which effect dominates is a little bit in the weeds, and we can discuss that later. But right now, let's just, for simplicity, assume G has degree at most 2 in each variable. Okay, so let me tell you a little bit about this protocol. Okay, so from the verifier's perspective, this sum check protocol acts as like a reduction. Apologies for any background noise, but that's just what I have to deal with today based on my location. So from the verifier's perspective, the sum check protocol is like a reduction from the hard work of computing this big sum. So summing, 2 to the n evaluations of G, so this is summing 2 to the n evaluations of G, to the potentially much easier task of evaluating G at a single point. The only wrinkle is that now R comes from the whole field, right? So, if the verifier were to compute this sum directly, this sum involves 2 to the n evaluations of G. So that's a lot of evaluations of G. So in applications, often this 2 to the n would be like the size of the circuit or something. In a snark for circuit sat, often, the sum here has one term per gate in the circuit. So, this 2 to the n evaluations of G might be circuit size, like in a snark for circuit sat. Although we won't talk about these applications for a little bit, that's how you should think of 2 to the n. So, there's enough terms in the sum that the verifier doesn't want to compute the sum on its own. But imagine for the time being that the verifier is willing to evaluate G at a single point. So not 2 to the n is too much, but 1 point is not too much. Okay. And so there are n rounds in the sum check protocol, 1 per variable that the polynomial G is defined over. Okay. And the message that the prover sends in each round is a univariate polynomial. So it's kind of a funny protocol. I've never seen it before. Each round, the prover sends a univariate polynomial. Right. So you're summing the evaluations, of an n-variate polynomial, but each message just focuses on one of those n variables. Okay. And this univariate polynomial, let me call it SI, has degree at most 2 in its one variable. Okay, which means the prover can specify SI, by just sending 3 coefficients or something. So it can send most people are probably comfortable with saying, just sending the coefficients like, say the coefficients are like A0 plus A1 times X plus A2 times X squared, so it could just send the 3 coefficients in the standard monomial basis. Or it could send like 3 evaluations of SI. That's also enough to specify this univariate polynomial. Okay, and so you can pick any 3 evaluation points you like. I happen to pick 0, 1, and 2. They are simple enough. And so, what this means is the total proof size in the SumCheck protocol is, something like 3n field elements, right? Because there's one round for each of the n variables that G is defined over, and the prover sends like 3 coefficients in each round. And actually, it turns out that the prover does not need to send SIO1. This is kind of a low-level optimization, so really you can get the proof size down to 2n. But that's way in the weeds, so let's not worry about that right now. Okay, so that's the outline of the protocol. So the total verifier time, turns out to be, like order n field operations, plus the time to evaluate G at a single point. So this is compare to the cost of computing the sum on its own. So of solving the problem on its own with no prover. That requires like 2 to the n evaluations of G. Right. So again, think of 2 to the n like in a SNARK application as like circuit size. If the prover is claiming to know a satisfying assignment for some circuit, and so this order n field ops would be like order log circuit size. Right. So to make this a little concrete, you might have a circuit with like 1 billion gates. So that's like 2 to the 30 is like 1 billion. And so the verifier doesn't want to do 1 billion, if it didn't have access to a prover, it would need to do like 1 billion field ops just to compute this sum. Even if it knew the satisfying assignment, like just to evaluate the circuit and confirm that the claim satisfying assignment indeed satisfies it would be 1 billion field ops. And log of a billion is like 30. So this might be, even if you factor in the leading constant of 2 or something, this might be 100 field ops or something. Right. So we're reducing like a billion evaluations of G down to the verifier doing just like 100 field ops and evaluating G at one evaluation of G. Okay, so the verifier is like saving a lot of work by going to the prover and saying, hey, I don't want to compute the sum on my own, do it for me, and I'm just going to check your proof. And checking the proof takes only like 100 field ops or something and requires 1 evaluation of G rather than a billion. So that's the SumCheck protocol. Okay, now, people who have seen like popular SNARKs, like Gross16 or Planck or Starks or something, often find it harder to, in my experience, to understand what's going on in this protocol, because in this protocol there is no cryptography, right? This protocol is what's called information theoretically secure. So it's not the case that the prover winds up succinctly committing to large vectors or anything like that. This is purely an interactive proof in like sort of the precise formal sense of information theoretic security, where all the prover's doing, to generate this proof is basically like multiplying and summing field elements. There's no hashing, there's no group operations, nothing. And so, yeah, we'll see how the protocol works in a minute. But from the verifier's perspective, it's pretty nice because the amount of work the verifier does is roughly logarithmic in the number of terms being summed, and from the prover's perspective, it winds up being very nice, in part because there's no expensive cryptographic operations. Now, without any cryptography at all, it is an interactive protocol. It has 1 round per variable of the polynomial being summed. But it's a public coin protocol, which means you can apply fiat Shamir, which is cryptographic in nature, to render this protocol non-interactive. Okay, and
there is a question. Let me know when's a good time to pause. Okay. The question is basically it's like, it sounds like this reduces the cost from 2 to the n to n plus t to evaluate our G of R. But isn't that cost p equal to 2 to the n from before? I think the
Yeah,
question is essentially like, how does this actually speed things up?
yeah, that's great. It's a great question. So the question is essentially, is getting this one evaluation of G really any simpler than getting the 2 to the n evaluations of G that, suffice to just solve the problem with no prover? And the answer is, if G were specified via its list of 2 to the n evaluations and there's no simpler specification of G, then you're exactly right. There's no benefit for the verifier to the sum check protocol. But it will often be the case that that's not how G is specified. Well, I mean, it will basically always be the case that that's not how G is specified. And so the verifier is saving time. Unfortunately, this is a little hard to see without just seeing applications. And so, I always have this struggle when I present the sum check protocol. Like, should I cover the details of the protocol and then cover applications, or should I cover some applications before we see how the protocol works? Because it's just hard to grok, why the protocol is saving the verifier costs and stuff.
Yeah,
But
I think it's completely fine to do the applications first. Just remind us regularly that you are papering over details that you plan to come back to later. I think is helpful.
Great. Okay, so let's see a couple applications then before we see how the protocol works. Okay. And so I'm going to try something new today, which is the book. First application it covers, I think, is like triangle counting or matrix multiplication. But I want to try something new, which is to dive right into something snark relevant. Which more and more, I think the group winds up having people who participants who do have some background in snark design, and so these applications are not the most important in snark design. So I think I'll just dive into one, which we'll cover again in a few weeks in more detail, but which is basically Spartan for R1CS. Just to give a sense of why this evaluation of G can the verify can often obtain it quickly or something like that, and why n is like log circuit size, and so forth. So the point of Spartan is meant for the prover to prove that it so P claims to know a vector Z in field to the n, say capital N, such that AZ, and I'll tell you what A is in a second, but AZ entry-wise product. So AZ is a vector. AZ entry-wise product BZ equals CZ. Okay. And so what these A, B, and C's are, these are three public matrices. So that is the verifier somehow knows these matrices. And let's say they're m by n matrices. Okay, so each row of the matrices represents a constraint. So m constraints, each of the form. So just taking away the matrix notation, looking at one rank one constraints, each would be of the form like if this is row I of A, so this would be AI inner product Z times BI inner product Z equals CI inner product Z, right? So this is just another way of writing, this is like the matrix notation of this. So we have m constraints, each of this form. Okay, that's the setup. All right, and the way Spartan will work is the following. So let's let well, maybe, okay, sorry. I don't want to overload notation here. Let me change let me make this capital A, capital B, and capital C. Okay, sorry. So let me let me call little a times z, little b times z, and little c times z. Okay, so the claim here is that like little a entry-wise product, little b minus little c equals the all zeros vector. Okay, so I've sort of written R1CS three ways now. We have it in matrix form. We sort of have it, in robot, constraint form. And now we have it kind of in matrix form again, but where I just replaced like a matrix vector product with, a little letter, just so I didn't have to keep writing out the matrix vector products. Okay. So this is what the prover's claiming. Okay. And so now we get to sort of the conceptually most thing about applying sum check that takes the most getting used to, okay, which is the little a, little b, and little c. These are vectors of length m. So they had one entry per constraint. Yeah, but we don't want to think of them as vectors of length m. All right, like why not? Because the reason why not is we want to apply the sum check protocol. The sum check protocol somehow needs a multivariate polynomial whose evaluations we want to sum, right? So somehow I need to turn this equation here, which has, involves vectors of length m, into a statement about sums of evaluations of some polynomial over multiple variables. Okay, how do we do that? So we need to interpret our vectors not as vectors, but as functions. So let's interpret these vectors as, what I call evaluation vectors. So that is a list of all evaluations of functions over domain 0, 1 to the n, log m. So actually, sorry, I think I might have, I think I wanted capital N for the number of columns and, yeah, sorry, let's say capital M for the number of rows. Sorry, so we have our length capital M vectors, sorry about that, and those correspond to functions over domain 0, 1 to the little m, where little m is log base 2 of capital M. So that is, if you're not comfortable with logarithms, capital M is 2 to the little m. Okay, so let me give an example. So let's say, A has, I'll give this the smallest example that's sort of meaningful. A has 4 entries, say 3, 4, 1, 2, and we're going to instead interpret this vector as listing like a of 0, 0, a of 0, 1, a of 1, 0, and a of 1, 1. Yeah, and so similarly, if a had 8 entries, we'd be thinking of this as a of all zeros, 3 zeros, a of 0, 0, 1, a of 0, 1, 0, a of 0, 1, 1, a of 1, 0, 0, a of 1, 0, 1, a of 1, 1, 0, and finally a of 1, 1, 1. Yeah, so we're again we're interpreting a vector of size capital M as all evaluations of some function defined over log capital N bits. Yeah, does that make sense? Any questions about that? Okay, so once we do this interpretation, and I'm abusing notation here, I'm using little a to denote both like a vector of length 8 and a function whose domain is 0, 1, to the 3. But there should be no confusion, and they're really the same object. It's just, how we're interpreting it. The nice thing is, once I'm talking about a function defined over 0, 1 to the little m, I can talk about its multilinear extension. So the multilinear extension um, of little a, because remember, little a we're now thinking of as a function whose domain is 0, 1 to the little m, and so it has a m-variate multilinear extension. Okay. And so now, what the claim that, so the claim that so the prover's claim here, that a entry-wise b minus c equals 0 is equivalent to the claim that a twiddle of x times b twiddle of x minus c twiddle of x equals 0 for all x in 0, 1 to the little m. Okay. And so, we almost are done. We're almost ready to apply sum check. It doesn't quite work, unfortunately. This is part, the fact that this doesn't quite work is part of why I always have a little bit of trouble giving a good application for the sum check protocol, like on day, before I even describe the protocol. If this were to work, life would be great, and like everybody, I think, would get very comfortable very quickly with how to use and apply the sum check protocol productively. The fact that this doesn't quite work just makes it a little harder to see how one should apply it. But okay, so let's let g of x just be a twiddle of x times b twiddle of x minus c twiddle of x. Okay, so this polynomial has degree 2 in each variable, which is exactly how I told you to think of sum check is, we want to sum up all evaluations of a multivariate polynomial which has degree at most 2 in each variable. So this is the sort of polynomial you should have in mind. Okay, and so if we apply sum check to g, what that will let us do is it'll let us compute, all evaluations of g over the hypercube. Okay, and so something that's easy to see. So let me call this thing here star. If the prover is honest, then then g of x equals 0 for all x in the hypercube. Okay, so if the prover is honest, so if P's claim is true, this sum will equal 0. This equals 0. Okay. So the reason this attempt does not quite work is that it's possible for this sum to be 0. So this sum might be 0, or how do I, sorry, not star. Let me call this. Sorry about this. Let me call this sum star star. But the prover's claim is that g of x equals 0 for all. So this claim is equivalent to g of x equals 0 for all x in 0, 1 to the m. Okay, so if star holds, then star equals 0. Unfortunately, the reverse is not true, right? Like star might hold without star holding. Right. So, again, if star holds, then every term of the sum is 0, so the sum equals 0. Okay, but if the sum is 0, it doesn't mean that every term is 0, right? If n equals 1, like you could have g of x equals minus 1 and g of x equals plus 1, and then the sum over x, the g of 0 equals minus 1 and g of 1 equals plus 1, and then the sum over all x of g of x is 0. And yet it's not the case that that star holds. So it's this star is equivalent to g of x equals 0 for all x in 0, 1 to the m, but in this example m equals 1. Yeah. So so we almost were at the point in attempt 1 where the sum check protocol gave us exactly what we wanted of confirming that A, B, and little b, and little c satisfied all the constraints. The problem is, that summing G's evaluations over the hypercube is and confirming that sum is zero is not equivalent to every single evaluation over the hypercube being zero, because you can get cancellation where non-zero things wind up summing to zero. And so, how do you deal with that? Yeah.
For the attempt number one, can I ask a small one?
Yeah.
Uh, at the moment where you indicated that the max degree is 2 for the g of x, could you say a couple of words if this degree connected with small m, do they influence each other? And the other question to the same thing is if we multiply a of x twee dot with b of x twee dot, won't it quadruple the max degree of each of them?
Yeah, great. So this g of x has degree 2 or at most 2 in each variable, but the number of variables is m, little m, which is log base 2 of big M, which is big M is the number of R1CS constraints. Okay, so they're unconnected, right? Like no matter how many constraints there are, the degree of G is 2 in each variable. But the sum check protocol, the prover sends a degree 2 univariate polynomial in each round. And so there's 1 round per variable. So this little m is also the number of rounds sum check. Okay, so the more constraints there are, the more rounds of sum check there are, the bigger the proofs get. Okay, but in each round, no matter how many constraints there are, what the prover's sending is a degree 2 univariate polynomial. So that's only just like a couple field, 2 or 3 field elements in each round. Does that?
Yeah, and max degree of a twiddle, for example, is 1. Am I correct?
Yes, like by definition, because these twiddles mean multilinear, which means degree 1 in each variable. And so that's why, if I multiply 2 multilinear things together, I get something of degree at most 2 in each variable, right? Like just as an example, like x1 times x2, let's say that's a twiddle of x, and b twiddle of x is like x2 times x3. If I multiply these together, I get x1 times x2 squared times x3, and the degree is at most 2 in each variable, right? Like you can just see, for each variable, you get degree at most 1 from a twiddle and degree at most 1 from b twiddle. So you multiply them together, you have degree at most 2 in each variable. Does that make sense?
Yes, thanks a lot. All clear.
Great. Yeah, great questions. Any other questions?
One more coming.
There's one more question?
I think so. I got a request to speak. I'm waiting for him. There we go.
Okay.
He's coming.
Can I ask a question?
Hi.
Did you hear me?
Yes, I can hear you.
Hi. I have a question about the. Okay, thank you very much. So I have a question about the degree. So when we do the sum over the Boolean cube, so the degree normally don't have. We can reduce it to the degree 1 because we replace just by 1 or 0. So if you have a degree 2, it's x squared, for example, it's like x1 squared is like x1. So I don't know if it is possible to make a map from, for example, doing a sum check on polynomial of degree at most 2 to a multilinear degree polynomial. So this is just my question.
Yeah, great.
I don't know if...
No, so it's a great question, and you're actually foreshadowing exactly how to fix. So attempt 2 will actually be the final attempt. Will use exactly your observation or proposal. So, but let me just highlight the issue here. So the observation you're making, which is totally right, is that, if I only care about X in 0, 1, to the, I guess, number of variables right now is M. So then for any I, like xi squared is the same as xi, right? So what you're observing, and I'm just summarizing your observation for the group at large, is like, imagine like g of x were, x1 times x2 squared times x3. The observation is, if I just replace x2 squared with x2, so let h of x equal x1 times x2 times x3. I do not change, G's evaluations at all over the hypercube. Right? As long as I only evaluate G and H over 0, 1 to the M, then, replacing every even exponent with, replacing any exponent greater than 1 with 1, I didn't change anything. Okay, so the problem with doing this is that in general, G of X or G of R might be really fast to evaluate. Remember, at the end of the sum check protocol, the verifier has to evaluate G at a single random point R. And so G of R might be really fast for the verifier to evaluate, while this multilinear version, H of R, is not. And so in general, you may well have this be doable in something like, like order M time. Remember, think of M as something like circuit size or number of constraints or something. Let me call it number of constraints. Log number of constraints, little m, while H of R may take time order capital M, which is 2 to the little m, which is like number of constraints. So there might be an exponential difference in verifier time if you just replace G, which has degree, say, 2 in each variable, with the multilinear thing that agrees with G at each variable. At each point in the Boolean hypercube. So it's a great suggestion, and the relationship between these two is exactly how we are going to proceed in attempt 2. But they are not, that's the big difference between non-multilinear things and multilinear things, is like sometimes you just have to go to the non-multilinear thing to ensure that it's quickly evaluable by the verifier at one point. Because the multilinear thing may take time linear in the size of the hypercube rather than the number of variables of the hypercube, which is logarithmic in the size of the hypercube. Does that make sense?
Yes, thank you. Maybe I have another question about the sum check, or let's say the sum over the cube for a multilinear polynomial. I see that there is a link between the coefficient. We can build a circuit, and every operation in each gate is just, for example, multiplying by 2 and adding the other. I can send you what I found. So at the end of the day, we keep doing the same operation. Or I'm talking just about the multilinear case, not the general case. I don't know if it works. And at the end, we find the sum over the hypercube. So this is why I was wondering if there is a possibility to map maybe this not multilinear case to the multilinear case. But at the end of the day, thank you for your at least it gave me the sense why it doesn't work. Thank you.
Yeah, great. So the sum check protocol is more general than I presented here, where this sum can in general be over any product set. So in general, we can replace 0, 1 to the m in the protocol with h to the m for any h in the field, subset of the field. So all that matters really is that, it's treating every variable the same, so you're summing over, the same set variable by variable. and so generally speaking, there are trade-offs. So if you use, h equals 0, 1, 2, like generally speaking, what you'll wind up with, and I'm glossing over some details here, but the number of variables m will become like log base 3 of the number of constraints rather than log base 2. And so you get fewer variables, but the degree of g in each variable will be 3 rather than 2. So ultimately what that means is, you wind up with fewer rounds because there's one round per variable, so fewer rounds of sum check, but like a higher degree polynomial sent in each round. So like a degree 3 rather than degree 2 polynomial sent in each round. Okay, and generally speaking, the proof size is minimized at the extreme case where h is 0, 1 to the m. But if you let h be bigger, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, whatever, you sort of get fewer rounds, but the decrease in number of rounds is more than offset by the increase in what's sent in each round. Okay, but the trade-off space gets more complicated in SNARK design. Sometimes having a lot of rounds is annoying for certain reasons, especially if you start recursing SNARKs or something like that. And so this trade-off between number of rounds and length of message sent in each round kind of remains to be fully explored, I think. But like typically today, people just work with the hypercube because it's just kind of simplest and does lead to the shortest proofs overall, albeit with the most number of rounds. Other questions?
Okay, thank you. Maybe I have another small question. In the practical case, what is the most used, let's say, polynomial, the multilinear polynomial or the general case? Just because I don't know in all the implementation. So
Yeah.
this is the first question, and the second question is about: is there any way to translate the sum check to a circuit? For example, I don't know, the sum over the hypercube, to map this operation of summing over the hypercube to a circuit, and after that we can just apply, for example, the GKR protocol. This is my second question, and thank you.
Yeah, great questions. Yeah, so okay, so in practice, if you are using the sum check techniques anyway, which are becoming more and more popular, the typically multilinear extensions are the most common, but like remember, this G is not multilinear. Okay, it's made up of multilinear things, right? So G itself has degree 2 in each variable, but we obtain degree 2 by multiplying two multilinear things together. So that's typically how things go in practice. Is you'll take two or more multilinear extensions, multiply them together to get some non-multilinear thing, and apply sum check to that. Okay, that's what's most common in practice. And actually, this is a good time for a quick aside. I think this is actually quite important, which is if G is multilinear. Okay, like again, in applications, it's basically never multilinear with very few exceptions. But if it were multilinear, then summing up G's evaluations over the hypercube is actually equivalent to up to some scaling factor, which don't worry about, of evaluating G at a single point, a very structured point. Okay, so let's call this an exercise. This actually is an exercise in chapter 4, at the end of chapter 4. So let's, I'll leave it as an exercise, but like if G were multilinear, okay, then the verifier on its own could actually compute the sum via a single evaluation. at a very special point, namely, like a half, this of course assumes the characteristic of the field is more than 2, just because in the field of characteristic 2, 2 has no inverse. The characteristic of the field is 3 or more. Okay, so that's why, it's the point of sum check from the verifier's perspective is to reduce computing a big sum, over 2 to the m terms down to evaluating G at a single random point. If G were multilinear, that reduction would more or less be useless because you could just compute the sum with a single evaluation of G. So that's why it only ever makes sense to apply sum check more, with, again, like 1 or 2 exceptions, which I won't get into here, to a non-multilinear thing. Okay, but again, the non-multilinear thing is typically obtained by taking 2 or more multilinear things and multiplying them together. Okay, and then your other question is basically like, can I take this R1CS instance and turn it in, like, is it equivalent to circuit, like a circuit sat instance? And the answer, I'm going to give a 1-sentence answer because, it's sort of not directly related to, understanding the subcheck protocol, which I guess should be the focus today. You can view R1CS as a sort of generalization of circuit sat, where Z would be storing like the gate value, for each gate in your circuit that you care about. Okay, and then there's like one constraint per gate in the circuit. So like if a gate is a multiplication gate, you would want like, like the circuit input to that gate, like Z of like the input to that gate, input 1 times Z of input 2 to that gate, minus Z of like, the value assigned to that gate equals 0, right? So you have a constraint, per gate capturing that, like the value assigned to that gate is correct given the values assigned to the inputs to that gate. So in that sense, this snark that I'm sketching to you right now is solving a generalization of circuit sat. And in another sense, you can sort of turn any one R1CS instance into a kind of trivial circuit where there's like one output gate per constraint, but that transformation might introduce major overhead. So let me leave it at that. So short version, you can view the protocol I'm describing now as solving a strictly more general problem than circuit sat. You can also view circuit sat as like, solving a special case of R1CS or something, or sorry, solving so they reduce to each other, but that doesn't mean that the transformations between the two don't introduce major overheads. Okay, hopefully that was somewhat helpful as a response. Okay, so I guess I will move on now since we're trying to minimize the amount of time on questions, but I think every question today has been directly related to what we're talking about. So hopefully
they totally have been. We have one more question, so he's on stage. Do you want to go ahead and ask it?
Yes. So the question I had is, do we really care about evaluating a multilinear polynomial if we have access to techniques like polynomial commitment, where we can just ask for a evaluation proof instead and avoid having the verifier do all the work of doing that evaluation? Like, it seems like to me that that's why we're avoiding multilinears, is so that we don't need to do this hard evaluation.
Yeah, exactly. So I mean, you're not misunderstanding anything, but that also doesn't mean there's no point to sum check, right? So all right, so let me try to answer the question this way. So remember, here we had little a was a times z, little b was b times z, and little c was c times z. Okay, and so the claim that we started with was for all entries in 0, 1 to the m, little a, a twiddle of that, of x times b twiddle of x minus c twiddle of x equals 0. Okay, so this is a claim about, 2 to the m inputs, you know, to A twiddle, B twiddle, C twiddle. Yeah, and then you know, if we applied sum check, and again, this was attempt 1, it didn't quite work. But you know, if it did work, like just imagine it did work, where g of x was A twiddle, you know, of x times B twiddle of x times C minus C twiddle of x. We apply sum check. You know, now the verifier, you know, at the end only needs to evaluate G twiddle at a single point, which it's evaluating G twiddle of R. You know, of course, you can do for V to learn A twiddle of R, B twiddle of R, and C twiddle of R. You know, because then G twiddle of R, sorry, G of R is just, you know, this times this minus this, and so you know, so suppose A twiddle, B twiddle, and C twiddle were committed with the polynomial commitment scheme, right? Like this, getting these evaluations is exactly what the polynomial commitment scheme lets you do, right? So they're good for giving you like one evaluation. So sum check was still useful, right? Like rather than needing to know capital M evaluations of A twiddle, B twiddle, and C twiddle, we now, the verifier only needs to know one of each. So that was still useful, right? Like, and then it, you know, if these were committed, it can just get it from the commitment. Okay, and more like with Spartan, you know, like the A twiddle, B twiddle, C twiddle turns out will not be committed. And this is part of the power of sum check, because if you know, univariate polynomial based snarks would commit these things. They would be univariate extensions instead of multilinear ones, but they would be committed. Only Z twiddle would be committed. Okay, and so, you know, there's and what the way Spartan works is, you know, at the end of the first sum check, the verifier wants to know A twiddle of R, B twiddle of R, C twiddle of R, and their A twiddle, B twiddle, C twiddle are not committed, and so the verifier says, well, not a big deal. I'm going to apply sum check a second time to express A twiddle of R, it, you know, as you know, like another instance of sum check. So it turns out to be, we don't have to get into it right now, what the details. So let me say, I don't know, coming up G prime of X. So we can write a twiddle of R as some other sum checkable expression. And you know, at the end of this sum check, the verifier has to evaluate G prime at a random point R prime. And it turns out like G prime of R prime it actually is equal to, you know, something involving A. So let's not worry about the details here. Don't worry about this, but times Z twiddle of R prime. Okay, and so this evaluation will come from the polynomial commitment scheme used to commit to Z twiddle. Okay, so it's sort of it's like a double win, you know, for sum check. So like even if A twiddle, B twiddle, C twiddle were committed, it's still useful to use sum check to reduce the original claim, which was a claim about like one claim per constraint, to a claim about a single evaluation of each of the committed things. That was already a major reason to use sum check. But on top of that, by bringing in a second application of sum check, we don't even need to have the prover commit to A twiddle, B twiddle, and C twiddle, rather just to the multilinear extension of the witness vector. So those are two reasons to bring in sum check, and two reasons it's a useful protocol, even though we, you know, snark actually have access to polynomial commitment schemes. Does that make sense? Was that helpful?
Yeah, thank you.
Yeah, and you know, you often see the univariate polynomials, like not only would, you know, these A twiddle, B twiddle, C twiddle things need to be committed, but you need to, in order to confirm that, like, now they'd be univariate. So let me stick a hat over them. So, you get a claim like a hat of x times b hat of x minus c hat of x equals 0 for all x in, some roots of unity, like nth roots of unity or something in your field. And the simplest way to prove that, if I call this, g hat of x, this is all one, univariate, one variate. That's why I'm sticking hats rather than twiddles over these things. So the natural way to prove this with univariate polynomials is to say, and we've seen this before, this holds, for all roots of unity x, if and only if g hat of x is divisible by this vanishing polynomial. So this is what's called the vanishing polynomial for the roots of unity. Okay, and that's so what the prover will do in the univariate snarks is often like commit to the quotient polynomial, and then the verifier picks a random point r and confirms that this equality holds just at r, g hat of r equals q of r times the vanishing polynomial at r. And that's nice and simple, but and it's just one round of interaction or whatever, not even. But now the prover has to compute this quotient polynomial and commit to it. And yeah, people have done a lot of really clever things to sort of, not have the prover explicitly commit to the quotients or whatever. But at any rate, that's loosely what's going on. And so the nice thing about SumCheck is, you never have to deal with quotients. You don't have to compute the quotient. You don't have to commit to the quotient. All you do is apply SumCheck to these polynomials that extend vectors that the prover probably had to commit anyway, just to confirm that it's a satisfying assignment for the R1CS or whatever. And so the benefits of avoiding that quotienting is still sort of slowly being understood and internalized by the community. Good question. Okay. So let me tell you attempt 2, which is actually how Spartan works. Okay, and based on the time, maybe I'll just wrap up there. I definitely don't want to start covering, the internals of how SumCheck works at more than an hour into a session. So I'll finish covering this application, and I think that's a good amount of content for the day. Okay, so since there have been so many questions, great, wonderful questions, by the way. Let me try to remind everyone where we're at here. So, the prover is claiming that g of x equals 0 for all x in 0, 1 to the little m. Remember, this is like little m is like log number of constraints. And g of x is, as a reminder, little a twiddle of x times little b twiddle of x minus little c twiddle of x, where a was, capital A times z, little b was capital B times z, and little c was capital C times z. And yeah, if you just apply SumCheck to g, the problem is that it could be that g of x is not 0 for all these Boolean x's, but when you sum them all together, they cancel out to 0. So how to address that? So we've already seen a hint of how to address it. Let me state a fact here. Like, if g were multilinear, it's not, but if it were multilinear, then g of x equals 0 for all x in 0, 1 to the m is actually equivalent to g of x being the 0 polynomial. Right? So remember, multilinear extensions are unique. All right? So the all zeros polynomial, literally g of x equals 0. Everything maps to 0. Right? That clearly extends the function, has the right behavior over the Boolean hypercube, and it's multilinear. So the all zeros polynomial is the unique multilinear extension of the function that just maps the whole hypercube to 0. Okay? So imagine for a moment that g of x were multilinear. It's not. But if it were multilinear, if it were, it's not, if it were, then the prover's claim that g of x equals 0 for all x in the hypercube, could be checked by having the verifier pick a random r in the whole field and confirming that g of r is 0, right? Because, why is this the case? Like, if the prover's claim is true, that is g of x does equal 0 for all x in the hypercubes. Yeah, that's claim star. So if star is true, then, g is the all zeros polynomial. And so g of r evaluates to 0 for any r, for all r in the whole field. Right. And if P's claim is not true, then G is a multilinear polynomial that's not the zeros polynomial. And so now by Schwartz-Zippel, if you have, so by the Schwartz-Zippel lemma, if I pick a random r from the whole field, the probability that g of r is 0 is at most the total degree of g, which is just m since it's multilinear, over the size of the field, right? So, up to this small soundness error, which captures the situation that, g is not the all zeros polynomial, and yet I happen to pick one of its very few zeros. Checking that G vanishes over the hypercube is equivalent to checking that it vanishes at a random point. Okay. So to summarize where we are here, I'm giving you like the reasoning behind the attempt 2. I haven't told you exactly what attempt 2 is yet. So to summarize what I've said, if G were multilinear, the following protocol would work. We could just, V would just pick R in the field and evaluate G of R, and there would be no sum check. We would just be done. We reduced, confirming that G vanishes over the whole hypercube, which is the prover's claim, to evaluating G at a random point. We did, there was no, that's it. We'd be done. Done. Okay. The problem is G is not multilinear. Okay, so what we're going to do is let H be the unique multilinear polynomial. And there was a question like basically about, can you just replace G with this H? And the answer was, well, you can, and then life would be grand. But, G being fast to evaluate does not mean H is fast to evaluate. So let H be the unique multilinear polynomial. This is literally the H we were talking about before in response to the question, such that H and G do the same things over the hypercube. Right. And like, I gave an example, like if G of X were X1 times X2 squared times X3, then H of X would be just X1 times X2 times X3. The point being that, if you only care about points in the hypercube, replacing the square of something with that something doesn't change anything because 0 squared is 0 and 1 squared is 1. Yeah. So that's what's that, here's just a little example of what this H looks like, given a specific G. Okay. And so, what, so the, I just explained via this reasoning here that went through Schwartz-Zippel, I said, so if G were multilinear, V could just pick a random point and evaluate G at that random point, confirm the evaluation 0 and be done. Okay. Now, G is not multilinear, but H is, right? So, what the verifier is going to do is verifier is going to pick an R at random in the field and confirm H of R is 0, right? So this is just exactly my fact from before, except the fact now does apply because H is multilinear even though G wasn't. Okay, so the problem, which I also flagged in response to the question before, is the verifier, can evaluate g of r quickly at any desired point r, but not h of r. Okay, so how do we address that problem? So this is the actual protocol. So fact, this is the final fact we need, and then I'll give you the protocol. So the fact is that h of r can be written as a very nice expression of evaluations of g. So h of r is equal to the sum over all x and 0, 1 to the m of this equality function. I'll tell you what that is in a second, of x comma r times g of r. Okay, and so, this is the function that, so it's the multilinear extension of the function that, if x and r are in the hypercube, then the equality function, spits out 1 if x equals r and 0 otherwise. Okay, and so I think we talked about this function last time, right? I said you can evaluate this particular polynomial in time linear in M, which is logarithmic in like its input domain size, which is 2 to the little m, right? Remember, EQ twiddle of r comma m, we discussed this last time, was the product from I equals 1 to m of ri times xi plus 1 minus ri times 1 minus xi. And so, you give me any points that you want to evaluate it at, and I can just compute this expression in time order m. And so, how do we see that this fact is true? Well, remember, this is the sort of thing we're going to do like 100 times in this reading group, in this study group. Anytime I assert that two multilinear polynomials are the same, all you have to do is confirm that they're both multilinear and that they spit out the same values when you evaluate them over the hypercube, right? Because multilinear extensions are unique. And so all you have to confirm is that if r is in 0, 1 to the m, then the right-hand side is indeed h of r, right? Because the right-hand side is clearly multilinear, since, sorry, there was a big mistake there. To make the right-hand side multilinear, I need to be feeding x into g. Yeah, sorry about that. If I fed r into g, it would be degree 2 in r. But if I feed x into g, it's degree 1 in r, right? Because EQ twiddle is multilinear, and that's the only thing I'm feeding r into. So the right-hand side is clearly multilinear in r, as I'm only feeding r into EQ twiddle, which is multilinear. And so the right-hand side is multilinear. All you have to do to confirm this equality holds is to guarantee that, the left-hand side and right-hand side have the same evaluation behavior when r is in the Boolean hypercube. And what's happening there is, if r is in the hypercube, then EQ twiddle of x comma r spits out 0 for every x other than the one x that equals r. And for that particular x, EQ twiddle spits out 1, and what we're feeding into g is x, which for that x is r. So that's what we saw. This is basically just reiterating multilinear Lagrange interpolation. So you can take, so in summary, like I can express, and the unique multilinear polynomial that agrees over all Boolean inputs with the non-multilinear thing g as a nice weighted sum of evaluations of g at the points we care about, which is the Boolean ones. Okay, so finally, I'm ready to tell you the protocol, right? So, the verifier picks r at random from the field of the m, needs to check h of r equals 0, but h of r, we just said, is sum over all x in 0, 1 to the m of, let me call it t of x, where t is EQ twiddle of r comma x times g of x. So you just apply sum check to t. And that's it. That's how the verifier computes H of R and confirms that it's 0. Okay, now at the end of sum check, we do have a bit of a nuisance, which I did discuss before in response to the question of like, why is sum check useful even when we have commitment schemes? At the end of sum check, the verifier does need to evaluate this T of R prime, which is EQ twiddle of R comma R prime times G of R prime. Okay, and again, the verifier can get this evaluation in order m time, which is good. That's like log number of constraints or something. That's fine. We're happy with the verifier taking that much time. But G of R prime is a little annoying. That requires getting A twiddle of R prime, B twiddle of R prime, and C twiddle of R prime. Okay, and that is annoying because remember, like little a was A times Z, little b was B times Z, and little c was C times Z, and the verifier doesn't know Z. Like in snarks, like Z would be committed. Okay, but no worries. Since we're so far over time, I won't give you the details, but you can, as I briefly sketched before, you can write A twiddle of R as like a sum over x in 0, 1 to the log, length of Z of A twiddle of R comma X times Z of X, Z twiddle of X, right? This is just sort of, it follows from the same kind of reasoning we see over and over again here, where, I claim that some multilinear thing equals some other multilinear thing. This is the right-hand side is clearly multilinear in R because I'm feeding R into, or R prime here, I'm feeding R prime only into a multilinear thing on the right-hand side. So I just have to confirm that the left-hand side and right-hand side agree over all Boolean inputs. And that follows from the fact that A equals, A times Z. And so this is just like, their agreement over Boolean inputs I'll leave as an exercise. But it's really not trivial. It's immediate from the definition of matrix vector multiplication. And so you apply a second sum check again, to confirm, so it's like the prover is going to tell the verifier, what the prover thinks A twiddle of R prime is, and the verifier says, well, that's great. Like if you're telling the truth, I can perform my final check successfully in the first sum check applied to T, but I don't know if you're telling the truth about A twiddle of R prime. No worries, I'm going to use sum check to make sure you're telling the truth. And so I apply sum check to the polynomial. Let me call it S of X, which is in this case A twiddle of R prime comma X times Z twiddle of X, to confirm that this equality holds. And at the end of the second sum check, the verifier just needs to evaluate Z twiddle of R prime prime for a single point R prime prime, and here if Z twiddle was committed with the multilinear polynomial commitment scheme, this will come from the commitment scheme. Okay. All right, and there are actually some settings where the second sum check is not even needed because somehow the verifier can actually efficiently evaluate A twiddle, B twiddle, and C twiddle on its own. And that actually arises in this Jolt ZKVM, but the second sum check isn't even needed. But I won't get into those details. Okay. But that sort of arises because in Jolt, these matrices, capital A, capital B, and capital C, are so simple that it turns out that these vectors, you can sort of check these equalities like hyper quickly without a second sum check. Anyway, so yeah. So next time we will see how the sum check protocol actually works, but we covered this application in great detail. I'm not sure exactly how well it went, but the point is what was to see, like, what the cost of the sum check protocol translate into in Snark applications, right? So remember, so sum check, to compute sum of x in 0, 1 to the m of g of x, in applications, g often has degree only 2 in each variable. It can sometimes go a little bit higher, but let's just say 2. There's 1 round per variable. The prover's message is in each round is a degree 2 univariate polynomial in each round. So it's just sending like 2 or 3 group elements in each round. Okay, and the verifier, sort of as a result, runs in order m field ops, and evaluates g at a single point. Okay, and in practice, m will be like log. Is log number of constraints in your constraint system, and then like in the second sum check in Spartan, it'll be log like number of witness variables, number of entries in this witness vector z. So think of this as like the NP witness for the claim the prover is making. Remember R1CS, the claim is like, it knows a z such that AZ entry-wise product BZ minus CZ equals 0. So, you think of Z as the NP witness. So I think that's the main takeaway here is, in most applications of sum check, the prover time will be like order, number of constraints plus number of like length of witness vectors. And so, this is like maybe circuit size if you're dealing with circuits, or in R1CS, it's, like I just said, number of constraints plus number of witness variables. And in fact, like in Spartan now, we really do have like this order m plus n really is like 5m field ops. Okay, so I mean, like the hidden constant here is like not big. I think there's some estimated sum check costs out there that are like way too high. I've seen like over 100M or something, and that's just missing all sorts of simple optimizations. You can actually get this down to like a linear number of field ops for the prover, where the hidden constant is like 5 or something. Okay, yeah, so that's our first application of sum check. And next time we can actually see how it works instead of just how to use it. Okay, so let me stop there, but I'm sure there are some questions which I can answer, and then we'll wrap up for the day. Any questions?
None at the moment, but we should pause for a little bit. Here we have one.
So you said that one of the like benefits of Spartan is you don't need a commitment to sort of the witness Z, but if you look at like the sort of way you calculate little a twiddle, you end up doing a sum check that has in the sum like Z twiddle. If I understand correctly, you do need to do a random evaluation of the thing in the sum at the end of sum check. So doesn't that mean we do need to hold on to Z or commit to Z or something like that?
Great. So sorry. In Spartan, you do have to commit to Z twiddle. You do not have to commit to little a twiddle, little b twiddle, or little c twiddle, right? So you do not commit to a times z, b times z, or c times z. You only commit to z.
Okay, I see.
Okay. Yeah, and with univariate polynomials, as far as I know, you always have to commit to these 3 things, as well as potentially a quotient polynomial. And then, but your question did have another part to it, which is, doesn't the verifier in this second sum check at the end of it need not only z twiddle of r prime prime, but also a twiddle of r prime comma r prime prime? And the answer is yes. And I just glossed over that. Okay, so but in practice, there are two things you can do. So one is often these constraint systems have a lot of repeated structure where you're doing the same simple check over and over and over again, right? That's exactly what happens in like any ZKVM. You know, the prover kind of commits to an execution trace, which kind of captures everything that happened at cycle 1 of the VM, and then everything that happened at cycle 2 of the VM, and then everything that happened at cycle 3 of the VM. And like for each cycle, there's a relatively small number of constraints that sort of says, everything in the execution trace for this cycle happened correctly. And so these matrices turn into like the same, handful of constraints just once per cycle. So the same little thing over and over and over again. So in that case, the verifier will be able to evaluate this like on its own pretty quickly. So like number of field ops, for the verifier will be at most like, the size of one cycle's constraints or whatever. So totally independent of like the number of cycles you ran the VM for or something like that. Okay, so in summary, so that's one thing. It's like when your constraints have repeated structure, often the verifier can get this evaluation very, very quickly on its own, and you're done. Okay. Now, even in the case where the constraint system is like totally unstructured, okay, you can have these polynomials A twiddle, B twiddle, C twiddle committed in pre-processing by an honest party. Okay. And then the prover can, in the online phase, once this evaluation point is known, the point that the subcheck verifier needs to evaluate A twiddle, B twiddle, and C twiddle, the verifier can go to the prover and say, hey, prover, provide this evaluation to me and prove that it is consistent with the commitment. Okay, and you can do that as well. Now that you have to leverage typically the fact that, in practice, typically these matrices are very sparse, so are mostly zeros. And you sort of don't want to pay for the zeros. You don't want the prover's work to be proportional to the number of entries, including the zeros. You only want it to be proportional to the number of non-zeros. And we have ways to do that. And so you can do that with something called a sparse polynomial commitment scheme. So those are the two things. So, and this is what I was saying, I think last week. I think I said this last week in some random response to a question. Like some check-based snarks have two modes. I call them like uniform mode and non-uniform mode. Uniform mode means the constraint system that you're dealing with has a ton of repeated structure. And in that case, the verifier can evaluate, the multilinear extensions of capturing the constraints, at the necessary points on its own very quickly. Okay. And then in the non-uniform case, you just do something extra in the protocol where an honest party commits to those, I call them constraint polynomials in pre-processing. And the prover, like in the online phase, provides the necessary evaluations of those polynomials along with an evaluation proof. Okay, and there was some discussion, I think, both in the ZK Study Club Discord, but maybe also, I don't remember if we also talked about it in our study group's Discord or not, but like in Spartan for non-uniform mode, this whole evaluation proof for the constraint polynomials would be like 90% of the prover's time typically. Right, so there's a big difference between running in uniform mode versus non-uniform mode, right? You're going to get like an order of magnitude speed up for the prover if you're running in uniform mode, just because you get to avoid dealing with polynomial commitments to these constraint polynomials. Okay, so hopefully that answered your question, and despite the length of the answer was understandable. There are sort of two issues. One Spartan means the prover does not have to commit to little a, little b, and little c. The prover does have to commit to z. There's no way around that. And then whether or not the constraint polynomials are committed depends on whether you're dealing with repeated structure or not in your constraint system. But typically I'd say we do have repeated structure, and so uniform mode is fine.
And a quick follow-up to that. If you have like a lot of repeated structure, do we end up getting an A that has this like block diagonal structure that you were explaining to us last week, or is it a different structure?
Yeah, so the block diagonal structure, I think that did come up last week. You do get that with ZK VMs. I guess that block diagonal structure sort of comes up that also captures like anything data parallel, I guess. I mean, it's a little more general than data parallel, but anytime you sort of have, like the same computation being done independently on many different inputs, and you either you might or might not care about all of the outputs. Maybe you just wanted to do a simple aggregation on all the outputs. You'll wind up with something like block diagonal, where you'll have, constraints matrices A, B, and C capturing your small, well, I just overlooked, let me call it C prime. This is like a circuit or something. A, B, and C capturing, constraints capturing your circuit. And, they'll be looking like, they'll be completely zero. And kind of what's going on is like your Z for the whole thing will kind of everything will just be done like copy wise, right? So you'll commit like the gate values for this copy of C, followed by the gate values for this copy of C, followed by the gate values for this copy of C, or C prime, sorry. And then each little constraint system just operates on one copy, just because the copies are completely independent. And so block diagonal is like a natural way to sort of capture doing the same little thing independently on many different inputs. And it's also possible for the inputs to kind of overlap in very structured ways. And you'll still be able to capture things with the block diagonal constraint matrix. So maybe like, you have sort of two smallish inputs, X1, X2, fed to the first copy, and then X2, X3 fed to the second copy, and, X3, X4 fed to the third copy. And so forth. Same C prime and this block diagonal stuff can capture that as well. Where right, like the columns here are indexing like variables of the witness Z, and so even if there's overlap, it's still sort of pretty block diagonal. It would look like the constraints would look like this would capture like the first copy of C. And then there'd be, they'd kind of half overlap. They overlap in the columns, not the rows. So be like, what would it be then? Yeah. That would be the second copy. This would be my pictures are terrible, but there's sort of a half overlap in columns for each copy of C prime. So you just get to sort of VMs are sort of like the very definition of a VM doing fetch, decode, execute, fetch, decode, execute, fetch, decode, execute over and over and over again automatically leads to these sort of repeated constraints, where you have the same simple constraint system repeated over and over again. And basically, because the witnesses in these VMs are sort of listing everything that happens at each cycle of the VM. And, like cycle 5 of the VM just like doesn't really interact much at all with like cycle 10 or, 11 or 12, right? Like, only adjacent cycles interact. You wind up with, block diagonal like things, just capturing that lack of it. Like block diagonal is all about lack of interaction between various entries of the execution trace or the witness vectors. Was that a little bit helpful?
Yeah, thank you.
Great.
There's a question that says, is there a threshold for how simple A, B, and C need to be for the second sum check to be skippable like it is in Jolt?
I mean, I can kind of tell you why it's skippable in Jolt. It's like, let's go to the true block diagonal case. just because it's a little simpler. And so, everything is just sort of capturing lack of interaction between different, like, cycles of the VM or, copies of the simple constraints that's getting repeated over and over again. And so, when you have this sort of block diagonal situation, this non-interacting stuff, like each row gets indexed by like, so you have the same like simple constraint system, what I calling a C prime is like simple, but then you have a whole bunch of copies of it. And so you can index constraints by, like which, so Y will be like which copy of the constraint system are you in, but X is like which constraint within the simple one are you in. So which constraint within C prime. And then similarly, like witness variables will be indexed in a similar way by, like which copy are you in? So let me call it, I don't know, W comma Z. Again, Z will be like which copy are you in? And W will be like which variable within the copy. Okay, and then, the block diagonal stuff means, like two different copy variables just don't interact at all, right? Like you get a zero, like the matrix, the constraint matrices are just zero if, like Y, telling you the copy for the constraints does not equal Z, the copy for the variable. And so as a result, there's just, no need in the once, so the first sum check, what it does is it sort of collapses all the rows, that is all the constraints sort of into one constraint. Okay. So, like if your matrices, had like a row variable and a column variable, the row variable at the end of the first sum check is sort of fixed to this random value like R prime, right? And so that's like saying, I've sort of, taken like a random linear combination of all capital N constraints, and now I'm down to like one constraint. Yeah. And so this R prime, fixes, I sort of overloaded Y here, which was maybe a bit, this Y is not the same as this Y. So, so this is telling you now there's this sort of, collapse to one constraint. And that, so I've sort of collapsed the copy variable to like one copy. And so what's going on is I don't need two copy variables, one for the rows and one for the columns. I only need one copy variable. And once I tell you the copy variable for the row, I get to ignore all other copies other than that copy because of this. Okay, so what happens at the end of the first sum check in Spartan for Jolt is I've sort of told you what copy you're in, or sort of I've collapsed all copies down to one copy, and so all that's left for the second sum check is a statement so second sum check, like we still might use a second sum check in Jolt, but like the sum is only over like number of variables in the small constraint system. Which remember the small constraint system captures just one cycle of the CPU of the VM. And so like the first sum check is big because you're summing over like, which cycle are you in? You're summing over all the cycles. But the second sum check, you no longer have to sum over all the cycles. Right? You sort of, the first sum check kind of fixed the cycle, if you will, even though that cycle now lives in the whole field rather than the, Boolean hypercube. And so the second sum check, while the first was over, like constraints in the small thing, as well as, what copy of the constraint system you're in for the first sum check. The second one is only over, which variable you're in. Don't have to sum over copy. Okay, and so that should kind of be the case, whenever you have the same simple constraint system kind of repeated over and over again in either a completely non-interacting way or, minimally structured interaction like this sort of, partially block diagonal situation here, where like the second half of the input to, constraint copy I is the first half of the input to constraint copy I plus 1. So not a very clear or short answer to your question, but it's like whenever you do the same thing over and over again, you kind of don't have to tell me, which copy of the constraint system I'm dealing with more than once. Like just tell me what copy I'm in once and that's it. Other questions?
There's a question about, do you know any like supplemental resources for learning about these matrix representations of constraints that keep coming up in the examples?
Not so much. It's there's been like a lot of papers that well, let me pull up let me see something. So what is it? I'm just trying to come up with one reference that might be useful. Okay, maybe I'm not going to be able to come up with it on the fly. Okay, yeah, I'll give up. I'll reply in the chat. So I think there's generally been a bit of confusion about this uniform versus non-uniform stuff. And, the sum check based snarks just naturally have these two modes, but I think the univariate ones like don't necessarily. And so like the history of like univariate based snarks kind of went, Aurora was targeted at non-uniform constraint systems, but I think even if you had a uniform constraint system, like you'd still have to pay the same cost as in the non-uniform case. And so there was some follow-up work that basically like tried to do Aurora in the uniform case. So you didn't have to pay for these constraint polynomials, if the verifier could just evaluate them quickly. And with sum check and multilinear things, you kind of just get that without any effort at all. But for univariate things, you actually have to do some work to achieve it. And that's why there was a paper about this. And so you could, it might actually be useful maybe to look at that paper, since it, the problem with the sum check based ones is, you just sort of look at the constraint systems that arise, from these VMs or whatever, and their multilinear extensions are like trivially evaluable. And so like nobody writes much down about it. It just, it just works. And so it's a little harder to point to things, but so you can look at the Jolt paper. We didn't write down like every optimization there, like this whole thing about not needing the second sum check in Spartan for the R1CS and Jolt is not in the paper. That's like an optimization we noticed later and haven't even implemented yet. If you go back to the CMT paper or Thaler 13, actually maybe Thaler 13 is better. Well, so the CMT paper like works through some multilinear extensions, some specific, like constraint polynomials, if you want, constraint MLEs, as does Thaler 13. But you have to kind of know where to look in the papers, so that can be a little bit annoying. Trying to think. So in particular, if you look at Thaler 13, like there's a section on data parallel, which is actually in the book. So actually, you probably should just look in the book. There's a section on like optimizations for data parallel settings. And if you look over that, you'll certainly get a little more comfortable with the sorts of things I'm saying. You'll see that that the data parallel stuff sums over like one copy variable, one copy instead of two. So it's very similar to what's happening in Jolt. How we can get rid of the second Spartan sum check. And then I'll post in the chat some reference, because I'm blanking on the name right now, for like a follow-up to Aurora, which like tries to get like similar stuff, similar properties for like univariate SNARKs for R1CS. And then the final comment is like anything that uses air is all about, is by definition about like uniform constraint systems. Like it is a kind of uniform constraint system. So I don't know the best resource to look at to understand air, because like a lot of the theory papers just like define it without too much discussion, but like you can probably, but there are plenty like so if you watch some videos from any of the Stark based projects, whether it's Starkware or RISC-0, they probably have a pretty good videos on like what is air, like how to think of it, how air sort of directly captured, like it's a constraint system, kind of constraint systems, like directly motivated by VMs. And so yeah, this is sort of the best I guess the best I can say right now. So you got your multilinear stuff, you kind of have to read through various papers. Your univariate stuff, you can either learn about air, which is uniform by definition, or look at some paper on R1CS, which is not uniform by definition, and how if you kind of restrict your attention to uniform R1CS instances, you can kind of get the univariate techniques to have similar properties to what I'm saying here, where the multilinear ones kind of just naturally have, you don't have to do anything. These MLEs turn out to be very quickly evaluable with repeated structure. Other questions?
Yes, sir. I had a quick question about the intuition in the fact that if the way community's application of sum check is on the G polynomial, which is a non-multilinear polynomial, then what was actually the benefit of interpreting A, B, C as 2 to the power m evaluations of a polynomial at m points?
Well, it lets you apply. Yeah, so it did let you apply sum check again to reduce. The original claim was about m evaluations of stuff, because there are capital N constraints, and the claim is that every single one of those capital N constraints is satisfied, and so sum check lets you reduce the claim about all capital M constraints effectively to a claim about a random linear combination of those constraints, right? So like at the end of the first sum check in Spartan, right, like we sort of fixed the, it's like the first entry of a twiddle is telling you like which row are you in, which constraint are you dealing with, and the second is telling you which column are you in, that is which like witness variable are you dealing with. And so after the first sum check, we sort of fix the constraint variables to some fixed random value. And so that's like replacing all capital N constraints with like some kind of random linear combination of all of them. And it's nicer to have like one random linear combination constraint rather than capital N different constraints. Now the verifier's work is sort of not done yet. The second sum check in Spartan, if you need it, reduces sort of a claim about all witness variables down to, a claim about like a random linear combination of the witness variables. And at that point, you really are done. And so it's like, think of, the constraint system has got a row for every constraint and a column for every witness variable. The first sum check collapses the rows. The second sum check collapses the columns. And once all that collapsing is done, you wind up talking about the constraint system's, MLEs at a single point. And like, this is the sort of thing that maybe the verifier can get quickly on its own. If there's repeated structure, or can get from the prover if a twiddle was committed. And similarly, the verifier needs Z twiddle at a single point, and because it's only one point, the verifier can get that value from the commitment to Z twiddle. So it's like some check is collapsing like many different claims into a single claim, derived as some kind of random linear combination of the many original claims. And then typically that single claim is just easier to deal with. Yeah. And so like either because like the relevant polynomials are quickly evaluable at a single point, but not, it would not be quickly evaluable if you had to evaluate many points. Is roughly what's going on. Does that make sense?
Yes, sir. So is this, I'm trying to understand whether I'm understanding correctly. So is this the reason why the way the EQ tilde function was defined last class was in a different form, and today how when it was discussed, it was like it evaluates to 1 at x equals to r and equals to 0 otherwise. So is the two definitions are different? Is this because of this collapsing reason that
No, I
you
think
just
so. I
told?
think you're asking. Let me make sure I understand the question right. So I think you might be referring to. So today I said EQ twiddle of x comma r, is the multilinear extension of the thing that spits out like 1 if x equals r. If they're both in the hypercube, and 0 otherwise if they're both in the hypercube. And I think you're saying yesterday or last week, I probably defined it as like chi sub x of r, which again equals 1 if x equals r, and and r is in the hypercube. So there's such chi of x, for each x in 0, 1 to the m, there's a different chi sub x, and 0 otherwise. And these are just equivalents. The difference is just, do you consider x to be like an input to EQ twiddle, or like do you consider a different, do you consider like a fixed x, and EQ twiddle now depends on that x? I mean, it's the same. They're the same polynomials though, right? So like, EQ twiddle is, of x comma r is the product from I equal 1 to m of xi ri plus 1 minus xi, 1 minus ri, same as chi x of r, same thing. But of course, if I tell you x, like there's yet another way to write this. It's all equivalent, which is, you can product over the indices of x that are 0, and there you get a 1 minus xi times 1 minus ri. Just because if xi is 0, this thing is 0, and you can just ignore it. And I can product over, the indices that are 1 of xi, and there I get an xi times r, just because, if xi is 1, then this 1 minus xi is 0, and you can ignore it. So these are all the same, and it's just, Lagrange interpolation, it's sort of nicer, like you're summing over the x's, so f twiddle of r equals sum over x, so it's nicer to, I don't know, like I like to, emphasize that there's a Lagrange basis polynomial for each x, so I typically write it this way. But I could write it this way as well. It'd be the same thing. It's just less clear that there's a different Lagrange basis polynomial for each x now, since you're sort of getting each Lagrange basis polynomial out of EQ twiddle, but just by changing the first parameter to it. So I kind of go back and forth between them without thinking, based on whatever feels most natural to me in a given context. Is that what you were asking, and is that the answer to your question?
Yes, sir, it did. Thank you, sir.
Yeah, great question. It takes time to just get used to these expressions, these, kind of one variable at a time products, which, we haven't seen yet how the SymCheck protocol works or how to make the prover fast, but, this sort of expression gets exploited very heavily, and you just have to kind of get used to it and internalize it, and then internalize the fact that there's one factor of the product for every bit in X or whatever. Yeah. Okay. More questions? Okay, well, thanks for bearing with me today. Again, I don't really know how this went. It's a new thing I'm trying, to start with like the application of SumCheck to Spartan before we even see how SumCheck works. But hopefully this means next time when we do see how SumCheck works, you'll have in your head, hey, there's one variable, the number of variables is logarithmic in the number of constraints or size of the circuit or something. So there's one variable per bit in the binary representation of each constraint. We're always going to interpret like these vectors of length capital M as functions over domain 0, 1 to the little m, where little m is log of capital M. So that way we can take multilinear extensions and apply SumCheck to like a product of two multilinear extension polynomials or something. And so I think that will help make it a little easier to understand what's actually happening in SumCheck as we see how it works, to have seen what these parameters actually correspond to when you use it. But there is always kind of chicken and egg issue where I never know, like, should I present the protocol first if you don't know the applications, or should I put the applications first when you don't know how the protocol works? So we're trying it one way, and if it doesn't go well, next time to the group, I'll go back the other way. So thanks for being a guinea pig, and look forward to seeing you next week when we see how the SumCheck protocol actually works. So talk to y'all soon. See you next week.